Okay, so in this video we're going to do the final element of the previous lecture where we solved this problem. Basically it was a wind box with one of the panel, this one at the top, removed. Okay, so the geometry is about everything in millimeters. This is 1000, 400 and 200. Okay, so let me just create the points first. So geometry, points. So we do it this way. Let's say we start by the bottom, minus 100. So we have one at 0, 500, and 1000. Then we're going to have one at 100. This would be 500, and this will be 0. So the width would be on the Z would be 400. So let's say here, let me just do, since we're doing symmetric, let's do first minus 200. And let's start by the bottom. We have 0, 500, 1000. Now up plus 100. 500 and 0. Okay, now we go here to 200. It'll be 0, 500, 1000. And let's say that would be the last one. I'm hoping 500 and 0. All right, so let's see, Control A. So that looks about right. So we need, so let's say, let's do panels. So geometry, surface corners, method on point, and we can do okay, so it might look bad, may have done points that were not needed, all the one in the middle. No, this one, this one, this one, this one. We do the back. Now we do this one. So this one has panels everywhere, top and bottom. Okay. Now that one, that one, that one, that one. The bottom one, that one, that one, that one. Okay. All right, and the last one should be right over here. Okay, so that's the way I picture this problem over here, the geometry. Okay, so now we go, you can either go to the top menu or over here, but if you click on menu, let's say material, right click new, let's say you can put aluminum 2024, which I think is 75 gigapascals, Poisson ratio 0.3, that's all we need. Okay, cancel, so the material should be double click, so as it's highlighted blue means it's active. Now property, we need to define the new property. So the material is here. We're first going to define the shear panel. And from the previous video, generally that's what I do here, so that I remove any stiffness along the edges. You can put in all four, but generally these two. Here I put one for simplicity. Okay, and this should create our first property over here, shear. Now we're going to create the rod property. Also aluminum, area 1 to facilitate every calculation. And okay. All right, so now, so let's do model. No, mesh control, size on surfaces. Okay, select all. So we can do what, every 100? Or 50, that would be too many. Let's do 100, and then if we need to refine, we can refine. Just give us 2, 4. That might work. Okay. So I'm going to do mesh geometry surfaces. So select all. Okay, I'm going to do the shear property. That's it. Now we're going to do mesh geometry curves. I think we can do select all. Okay. And we're going to do the rod property. And okay. Then we go to tools. Check. Coincident nodes. Select all. Okay. If you want, you can click on preview. Done. Okay. Okay, if you want here, let's see, color, let's see, we put down one. The reason why I choose that color is because that's the color actually of the aluminum 2024 when it's treated for, when it's high pressure treated. So then you can go to custom tools, element update, color elements to match property. Okay, I don't know what color is this one, but let's say you should this one. Okay, I just choose weird colors, but okay. All right, so now let's first apply the boundary condition. So we could apply that boundary condition to all the surface or just to the lines. And then really we don't need this panel then. This panel should have 0. Any load because it's at the wall. So let's see, we can apply the model constraint. Let's see, we do it on the surface. So this will be clamp on that edge. That one here, okay. And fix. All right. Now we need to apply the loads over here. So let me do something. There's different ways. I think you could apply here the load in the middle node, but I don't know if that's going to deform this one, so it might affect the loading. So the way I will do it doesn't mean it's a correct one. I will try to create what they call a spider web over here. So it would be to connect this edge, this edge, this edge, and the other edge to our center node. So let's do that. So I guess custom tools or user tools. No. Custom tools. Meshing. Spider nodes. Spider curves. So spider curves, I select this curve, this curve, this curve, and this curve. And I should create a node over there. Okay, now the problem is to make sure that we don't select the one. All right, so let's see what's the name of the node created. Okay, we might have a problem selecting that node. Let me see something list or F6, that might work. Node ID, apply. Click the control and move it, and here we should have two. Oops. So okay, control A. Trying to find the numbers over here. Okay, it doesn't look like I'm going to be able to differentiate what would be the two numbers here. Okay, so I'm going to have to do it another way here. Control A. Let's see if I deactivate these properties here. That should leave just one node. And that's the node 16, looks like. Okay. All right. So let's do this. I don't think it should be anyone. The tools, check. Coincident nodes, select all, okay. Preview, okay, nothing should be coincident. Okay, so now we can apply the load at this node over here. So model, load, we're gonna put on the node, nodal. So let's say this will be shear force Vy. So I'm going to apply it here, should be, oops. So we had 16 over here, so cancel, let me deactivate this one. Model, load, nodal. Is that 14 or 16? Oh, I may have combined that one maybe, okay. Okay, let's see what happened. That's all we can do. So I think that load was 2000. Let's go back and check. Vy is 2000 newtons and okay. Cancel, control A, reactivate the elements. So let me file, save as. All right, let me create a temp folder here. And if I need to copy it somewhere, I can copy it somewhere later on. So let's say it will be model Fy only. Save. Can come here to the little gear, create, new, it's going to be static. You can say okay right away. Analyze. Okay, so finish. It looks like there's no errors. Let's go to F6 to limit out all those node numbers or no labels. Apply, okay. Maybe now, let's keep it just in case. Let's keep the geometry. F5. Let's first do criteria, deform, and here we're gonna look at the shear. So shear force average, shingle panel average stress. Since we put 1, that should be the same thing. And okay. So basically you see over here, you have 0 over here, 5, 5, 5, 5. About very small over here, 0, 0, 0. Okay, which is I think what we found when we did the classic solution with just study just for y, and we found 5 on this panel and 5 on the other panels. And basically what happened is that the theory basically gives us what? Is that if the load is applied in that direction, only the panels in that direction of the force, which means these side panels over here, this one, this one, this one, and this one will resist the force. If instead of Vy, let's say we had a Vz in this case, which panel will be resistant that shear will be this panel here and this panel here. Okay? All right, so that's good. That's actually better than my previous model. So perfect over here. So now let's see what can we do. So let's save this one. And now let's save file, save as, model, torque only. Save. So all I have to do, let's say, is to delete the results over here. All right, we need to delete the force. So let's see, loads, delete. Okay, I like to do this. You don't have to, but now model, load, nodal. So let's say now torsion. Here it would be this node over here, and it's a moment torque about which axis. So if it's about the x, no, around this, which is 1000 Newton meters, so which is 1000 times exponential 3, because it's 1000 times 1000. Okay, so if you want, let's put another 3 zeros, because we move meters to millimeters. And okay, cancel. So that will be our new model. File, save as, model T only, save, yes. We close all this figure here. So we do the analysis again, we already created. Let's see, hopefully it takes the load. Okay, so this will be our model over here. Let's do one thing first. File, open. Sorry for that. Let's go to this one here. And we also, remember we calculated the loads on the flanges. So let's maybe create a group, new, let's say top flange over here. So we're gonna take, so it's this one over here, is active group. Element on curve. I think okay, see if I can do something before I do that. Let me eliminate this one. So now I'm going to take only this one. Okay, so on that curve, that would be the top. Okay, hopefully that would work. Now group, new, bottom flange. Okay, and let's say group elements on curve. Let me select this one and this one. Okay, let me now. All right, so we're gonna do now F6. No, sorry, F5. And we're gonna look at the road axial force. Okay. Beam diagram. Okay. So here gives you, oh, this one a bit confusing, but if you come to the groups, right click, show active group, this will be the distribution for this one over here, which basically is minus this, but 4,720, but because of the mesh size is not very fine, I think we had from 5,000 to 0. You see, from 5,000 to 0, 2,500, and the bottom flange is the opposite. So this one is in compression, the top one, that's why it's going negative over here, and this one should be positive here because it is in tension. Okay, and that's because when you apply this load over here, this is moved up. So if this moves up, means this part here is going to bend this way, so it's going to be in compression, and this side, the lower part, is going to be in tension. So let me save this and let us go to the torsion only. Okay, so for the torsion, we have the result 12.5, 12.5. And so let's see what we had. Torque only. So 12.5, this is the walls, okay. So this should be this panel here and this panel here. Obviously this one is 0. Okay, this one here should also be 0 because it's not carrying anything, it's just the whole box. And this one, so this gives us about 10.25. This should be the same as this one, and this one should be the same as this one, okay? But one, it will be in that direction, see, with opposite signs. Okay, so generally for torsion, the results are not that the same, and I'm going to show, I mean, are not exactly the same. So 12.5, 6.25 first equation. Okay, so he had 3.125 and 9.375. So not, this one corresponds to this one here. So you see it's not exactly the same, and this one is not exactly the same either. All right. Reason of this, I think, is because here we assume that everything is ideal. And let's do F6. Sorry, F5. Contour. Okay. F5. Let's see what I'm showing here. Okay. And let's look at the deform over here. Let me remove the geometry. I mean, this is well exaggerated because really the deformation is almost 0, but basically what happens here is that you see that the deformation of this element here is a lot larger than any one of the other ones, even though it's very small. So, and that's because when we do the assumption, generally we assume, you see, this is bending, that the angle of twist of this section here will be the same as this section here, even though the panel is not there. So that creates, and since that is not the truth, there's something called the shear lag, which is basically this effect that you see this element deformation is a lot larger than any one of the other ones. And that's what introduces the small difference, so the difference on the shear panel flows for this side and this side. Okay. So these are 0, 0. So let's go to F5 criteria again. All right, and you should see it over there. Maybe let me show you something in my work. So F6, no, F5, deform. Let's look at the total translation of the same thing here. F5, contour, okay. Okay, I think that would be easier to see. You see that the deformation here, there is some change in colors here, the red, and that's what creates the extra deformation of this one. All right. But the assumption will say that the deformation here and here will be the same, but you know that because of the angle of twist, it's not really what is happening. So anyway, it gives you a good idea of the values anyway. So the 12.5 is good. This one should be what? 9.375, we get about 10.22. This one we get 2.26 over there, and it should be about 3.125. So that means that for the shear, we had exactly the same value. For the torque, is a little bit different because the load applied here on the flanges, on the transition from here to here, we assume is constant. But because the angle of twist of this box is not going to be the same as this one, that creates the effect of the shear lag. All right, so save. And now if you want, what we can do is just file, save as, model, Vy and T. So combine, save. So let's see if I keep this model, all I gotta do is all results, delete, okay. And now model, nodal, here. Is that the good one? Let me do here, cancel for a second. Let me limit out this one. Model, load, nodal, just to make sure I take the same one. So it was the same one, 14. And I add the load here of 2000 on the y direction. So you have the torque and the load. Reapply the elements. We run the case. There we go, F5. Okay, and these values should be pretty accurate, these ones and these ones, but we know that once we start moving here, it's not going to be that accurate because of the torque. But let's see, compare this one and this one. So what do we had? Combining both of them, let's look at panel 1, panel 2. 7.5, 7.5, and panel 2, 17.5, 17.5, and obviously the other one, panel 4, which is what? I think it's panel 4 is this one. Let's see which one was panel 4. No, panel 4 is on that side. So we get, oh, let's look panel 3, which is on that side, 1.875. We get this, 7.2, we get 8.125, okay? And here this one should be 0. Okay, so that's what we use to compare the hand calculation with the final element. And I will terminate the video over here.